All right, good afternoon. So welcome to this session. So this session, we're going to have a stop and go activity. It's going to be like Susan's session. What's happening is we will look at video of students making mistakes at the board, and I'm going to stop the video, and we're going to discuss it and see what kinds of strategies can we use in the classroom. So this is a real hands-on workshop-like session for this session. All right. So before we get to the videos, I want to do a little introduction. So it's okay to be stuck is part of the theme in this conference about empowering, right? So students feeling that it's okay to be stuck. And Ed Berger talked about this last night about impactful education. And I think one specific piece of that is when students realize that being stuck, making mistakes is part of the process, and that's something that won't faze them. They won't judge themselves as not being able to do math, but that it's just part of the process, and that they enjoy challenges, and that they can go and be stuck and make progress after that. So that's sort of the big piece here that I want to touch on. The next piece is the assumptions for this session. So let's get to those. Experienced users is the main focus here. So if you're a new IBL user, it's okay to be here. The idea here is that you've taught your IBL classes, you've taught some, and we're going to look at when students are stuck and how we handle those things. So we won't be going through sort of nuts and bolts basics of what an IBL class is and how to set it up. So this is a little bit more of an experienced user session. The other assumption I'd like to make is that we will focus on discussing options and not the answer, the singular answer to how to handle the situation. So those are the two main pieces. Stop and go activity. So let's get into the specifics of that. So what we'll do is we'll watch a video clip. They are at most a couple minutes long. I would like for all of you to act as if you're the instructor in the course. These video clips are from an Intro to Proofs class at Cal Poly and the number theory class that Mike Starbird taught in 2003. What I'd like for you to do is think of a teacher move after you've seen the video. What move can you make as an instructor? And then what we'll have you do is discuss with a partner what you're going to do. So you can't sit by yourself in this session. So if you're off in the corners, please move and join a table. Okay. This next slide is about some general strategies that have been applied. This is not to limit you, but just in case you need a seed to think about what you might do, here are three things. Small groups or pairs, where people have used think, pair, shares. The next item is the pause button. So some of us use the pause button in an IBL class, where if a student makes a mistake, say, hey, let's stop here and discuss some of the features that they can work on, and say, come back next time. And then you invite the student to either talk to you or they can just go and work on it. And a third option that has been used is getting the class to work on a specific task. So it could be, hey, let's all look at this special case and have everyone work through it, and then go back to a whole class discussion. So these are three common strategies. They aren't the only strategies. I'm saying these very broadly so that you can come up with your own solutions. And the last thing I'd like for you to do is think about, since if you're the instructor in this class, what very specific thing can you do and say? So think about very specific. What would you actually say to your class or to your students, or what task would you specifically give? So it's a very sharp session where we want to think about what you would do if this were your class today. Okay?
2 points as asking us if x and y are even integers, then x plus y is an even integer. So my approach to this is that it's a conditional statement. So x and y are even integers is proposition P, and x plus y is an even integer is proposition Q. So suppose P is true given that x equals y equals 2k, because that's the definition of an even integer. So x equals y equals 2k for singular k. So if we add x and y, we get 2k plus 2k, which equals 4k. And we get basically 2 times 2k. So the sum is just a scalar of the definition of an even integer, and a scalar of the even integer is still going to give us an even integer regardless. So based on what we proved in P, suppose Q is true, because x plus plus y is going to equal an even integer, then we can say the conditional statement P implies Q is true because both propositions here are true. Any questions? Okay.
All right, so I'll show that as a short clip. I'm going to show it one more time in case you want to see that piece again. So hold on.
2 points as asking us if x and y are even integers, then x plus y is an even integer. So my approach to this is that it's a conditional statement. So x and y are even integers is proposition P, and x plus y is an even integer is proposition Q. So suppose P is true given that x equals y equals 2k, because that's the definition of an even integer. So x equals y equals 2k for some k. So if we add x and y, we get 2k plus 2k, which equals 4k. And we get basically 2 times 2k. So the sum is just a scalar of the definition of an even integer, and a scalar of the even integer is still going to give us an even integer regardless. So based on what we proved in P, suppose Q is true because x plus y is going to equal an even integer, then we can say the conditional statement P implies Q is true because both propositions here are true. Any questions? Okay.
Okay, so take a minute to think of an idea how you might handle this situation. This is an intro to proofs class. It's about the 3rd week of the quarter. And after you've thought of an idea, check in with a neighbor. Okay, we're going to video 2, and we'll have a discussion at the end. Okay, same class, intro to proofs, a little bit later, and here we go.
So in theorem 2.1, it says 2.10, it says if x and y are both even integers, then 4 divides x and y. So we suppose that x and y are both even integers. So both x and y have to follow the form x is equal to 2k, y is equal to 2j, where k and j are both integers. Since they're both evens, the ones digit, so if we had 10, 12, 14, 16, 18, the ones digit must be either 0, 2, 4, 6, 8 to be even. So since they have to be 0, 2, 4, 6, and 8, when you multiply the last 2 digits, you get these values. And because all of those values are divisible by 4, then x and y must be divisible by 4.
Questions or comments?
Do we need to show it again? Are we? One more round? Okay.
So in theorem 2.1, it says 2.10, it says if x and y are both even integers, then 4 divides x and y. So we suppose that x and y are both even integers. So both x and y have to follow the form x is equal to 2k, y is equal to 2j, where k and j are both integers. Since they're both evens, the ones digit, so if we had 10, 12, 14, 16, 18, the ones digit must be either 0, 2, 4, 6, 8 to be even. So since they have to be 0, 2, 4, 6, and 8, when you multiply the last 2 digits, you get these values. And because all of those values are divisible by 4, then x and y must be divisible by 4.
Questions or comments?
We're going to transition to video 3, which will be the last clip, and afterwards we can have some people volunteer as we have time to share strategies that you might use in the classroom. So here's one more. This is from a number theory course. And let's watch the video. So this is Mike Starbird 12 years ago.
121, that's probably logically the next one, which is the existence part. Who did that? Alan?
Well, I just wrote down the diffusion algorithm here, and I say that we're given the m and n as an integer that n is greater than n. Therefore, we can include the q will be an integer of n divided by n, and r will be the remainder from the division by m and n. I give an example here, and the next step is that we can include that n times q will be less or equal than n, and r will be greater than or equal than 0, and less than equal than 10. That's pretty much it.
Okay, do you have any questions for Alan?
Just one thing, I don't think it said anywhere that n has to be less than m, because over here in 1.20, n is 45 and n is 33.
That's right.
Virginia?
I don't know how it works for other numbers too.
I would just say that it's not any integer of, because I mean, you could. Wouldn't it be at the least integer such that you get from us? I say that.
What do you think? I mean, I'm trying to get a sense of the crowd here. I mean, do you think this is a good proof or
One thing
not?
I'm just hesitant about is we're proving the division algorithm, and he used m divided by n in the proof. He used division in the proof, so I don't know. It's okay.
Ansel, what do you think?
I don't know, I got kind of lost. I don't know how you got to this conclusion.
Yeah, Stephanie?
I'm not sure what it means to be an integer of.
Well, it'll be like computer science. If you divide one integer by the other integer, and you will get something like maybe 4.6, and we take the 4 as an integer. Pretty much.
So we give it. Sorry.
I'm very bad at vocabulary.
Paul?
I was trying to do something similar. Since you said computer science, I was using a computer science mindset too. I guess you're a CS major as well?
Yeah.
All right. Because I was thinking that if you get two integers and then use the division operation, then you would get a real number. But if you take away everything after decimal, you would be given the integer. That's what you were thinking as well.
Exactly.
And then you would just get the remainder by using that newfound integer and then subtracting it to get the remainder. Is that correct?
Pretty much.
Can we use that? That would be cheating though.
I don't know. What do you think? I guess first of all, just to ground the discussion a little bit, I guess I'm a little trouble with just the very first line. Division algorithm, m equals nq plus r.
All right, so the student went up, clearly didn't get a proof of what he wanted. So now you're the instructor in the class, not Mike Starbird, so we'll take Mike Starbird out. So what are your options in the classroom at that moment in time? All right, go ahead and discuss. Okay, we have 5 minutes left in the session approximately. So what I think would be really useful is if we had people chime in to the whole group, and we have the 2 microphones. I'll say go ahead and line up. We can probably get a good number, 5 or 6 people to chime in. So please take a mic if you have something to share. Like what would you do? Or you can ask a question. So, and I would say line up so you don't have to wait. We can just go 1, 2, 3, 4 through your suggestions. So I encourage you to stand up and line up at a mic. PJ, yes.
So the main comment I have is, in every single one of those instances, I think the first thing I would have said was, what's the definition of, because that seems to be the big hitch for most of these things, is you're trying to prove something and it's not clear that you know what you're talking about in the first place, right? So what does it mean for like divisible in particular? Like what does divisible mean? Well, again, as in elementary school, you probably did just divide it and see if you got a remainder or not, right? But that's not what we typically would use in this class. So the definition was almost always what I would go to.
So you're saying ask the speaker, the presenter, to go back, to prompt the presenter, could you go back to the definition and talk about that?
Yeah, I would probably literally say, like, what is the definition of? And go from there. I really thought, like on the last example, and I suspect this is sort of what happened, is just leap right into the discussion from what his question was. Like, can I just divide it? Would that be cheating? And then go from there. And then, like, well, what's the definition of divisibility? Right, and so on.
Great.
So I'm speaking for our whole table up here, but specifically talking about the third video, we discussed how that is kind of an awkward moment, that like long extended awkward pause where some of the students are thinking this student has no idea what he's doing, but I don't want to be the one to be like, that's totally wrong. And some of the students are thinking, or sort of the inferiority complex thinking, I didn't follow that at all. That logical argument didn't make any sense to me, but he's probably really smart, so it's probably right, and I'm just missing something, and so I better just sit here and not say anything. So one thing that I've done kind of effectively about this is I'll kind of take an informal poll. One of us mentioned like using clickers in the classroom, but even I've done something where I just like have everybody shut your eyes. Now raise your hand if you think like, I agreed with that argument, that made total sense, we're good to go. Okay, now raise your hand if you're saying, I didn't follow that at all and I don't really know what to ask. And just kind of then you can gauge an awareness of where the collective students are on that. And then we discussed how the next thing that we might do is break into small groups, and you know, if we've come to a place where there's this argument and no one really knows how to deal with it or how to fix it or what suggestions to offer, break into small groups and tackle it in that way.
Great, great. So some great suggestions. All right, and then I'm glad you point out the awkwardness, right? So that's where the being stuck could go to, you know, a good experience or maybe a not so good experience, and the students can shut down. So we want to avoid that shutdown. And then Brian, you have an answer for that, right? No,
I think this is an excellent activity, but it's missing some information. So if this were to happen in my classroom, I probably would have had a reason that that student was the one doing this, and I would have maybe expected that this is their peers' response. So if my goals were to convince the peers that sometimes things will be up there, it'll be unclear if it's right or wrong, they need to be actually engaged in making that decision, then I might respond by saying, no, I'm not going to save you. You really are going to have to decide. If my goal was really to teach them more about the number theory, then I might pick up on that computer science metaphor and say, great, but computers have algorithms that humans decided, and what we're doing here is mathematics, and we want to understand how that works. So it's an interesting idea, but you haven't been specific enough. How would a human do this?
Okay, great. So you brought up some assumptions that our classroom dynamics will determine what we actually are using the presentations for, and then using the computer science as a segue into what is math for, and et cetera. So very nice. Thanks, Brian. All right. Is it 2:55? We have 1 minute. One more comment left. Here you go. Susan, yes.
So the first thing I thought is that if that student really is getting awkward, and hopefully you would know your student enough to be like, this kid needs to be cut loose, like, you don't need to sit up here while we're all debating this. Maybe that's great, you know, thank you for doing that. That brought up so many good questions, and I think we're gonna have a really good discussion about this. So why don't you sit down, and maybe we can all sort of talk in groups. I might, depending on where we are in class, I don't know about you guys, this always happens to me in the last 5 minutes. Hit the pause button, and I always blame myself. You know, I have some questions. I'm not sure I'm going to be able to formulate them right now, so maybe we can talk to our partners a little bit, think about what questions this raises and how we're going to address those, maybe come back tomorrow with a better explanation, then we can all talk about it. So that it doesn't, I think sometimes in my classes it devolves into like, that's not right, I don't know how to fix it, but you're wrong.
Right. Well, thank you for that. So I like how you're bringing the positive aspects. This brings up questions that we need to answer in order to progress. And that's really what this IBL, the inquiry-based learning, that the students can inquire, we can bring up the questions, and then pivot toward a productive effort. Very nice. Thank you, Susan. So, and thank you all for being here. If you want to learn more about our workshops where we do these kinds of activities and other activities to get you going on IBL, or you have colleagues who might be interested in, please contact me or visit our website. So that's it. Thank you very much. Enjoy the rest of the day.